Sefficiency in Sequity is a comprehensive water management approach. It focuses on adaptation, not mitigation. The presentation is in two parts. Here, the concepts that will be utilized to prove and develop sufficiency, which stands for sustainable efficiency, will be summarized. However, as a suggestion, it would be better if you first see the following two videos: Flaws in Water Management Frameworks and Water Management SIS. SIS stands for Sufficiency in Sequity. It should be keenly realized that an adaptation approach is fundamentally different from a mitigation one. Adaptation refers to the measures taken to manage the limited availability of appropriate water. Such a management must promote, as its priority, sustainable development of the scarce water itself in spacetime. In other words, policies of other systems of human activity should be functions of the availability of appropriate water. This idea, of course, is highly crucial for places that have water scarcity or pollution. To manage any system, including a water use system under adaptation, two broad performance indices must be considered. They are aggregative and distributive, which are generally considered as to be the efficiency and equity of a system. Focusing in this video on efficiency, let us first define it. Deborah Stone wrote that efficiency is thus not a goal in itself. It is not something we want for its own sake, but rather because it helps us attain more of the things we value. Hence, for the purposes of water management of a water use system under adaptation, sufficiency helps us attain more value from water with proper quality and in a sustainable way. Let us become clearer about the three pillars of a water use system. They are water quantity, water quality, and water benefits, or values. Their integration into one expression is one of the goals of the development of sufficiency, as will be seen. These pillars are measured, calculated, and estimated, which are complex tasks. For example, to find water benefits, we must quantify the values that a combination of water quantity and water quality have for the human and natural systems. The two attributes of water quantity are independent and are needed as weights from 0 to 1, which is a common practice. Sometimes it is easy to estimate. For example, quality weight of precipitation can be set as 1, meaning it is not polluted. Sufficiency in Sequity is anchored in various principles, such as water balance, which is the universal law of conservation of mass applied to water quantities of a water use system, which says the inflow is equal to outflow plus change in storage. It is a common practice to consider that change in storage is negligible, particularly for a proper period of analysis, such as a year. A water use system has only 9 water path types, each with greater than or equal to 0 water path instances. The schematic shows a water use system as a rectangle with 4 red water path types as the inflows and 5 black water path types as the outflows. The table shows the description of a water path type, and the equation gives the water balance for a water use system. 2 types of sufficiency will be developed, namely the in and out sufficiencies. For this reason, 2 types of water total is utilized. For in sufficiency, total water supply is utilized. However, for out sufficiency, its vital part, which is water consumption, is employed, and not the total outflow. Water consumption is defined as the amount of outflow that cannot be reused by the same water use system during a time interval. The rest of out is called non-consumptive water. The indices I and C are utilized for inflow sufficiency and consumptive sufficiency. It is of some interest to know that outflow of water use systems has 2 states, namely consumptive water and non-consumptive water. However, the output of other resources, such as fuel, electricity, and in a way, food has only one state, namely consumption. This is one of the reasons that water management is a complex business. The other 2 pillars of a water use system are the attributes of water quantity and are presented as 2 weights, namely quality weight and beneficial weight. The higher a weight is, more desirable it is. The multiplication of a weight with its water path instance filters its desired water from non-desired. The multiplication of these 2 weights gives the useful criterion of a water path instance. In other words, an inflow, or an outflow, in general has a useful part, which depends on the degree of its pollution, and its value for the stakeholder. Usefulness criterion is multiplication, not addition, of the weights because of compound conditions. It calculates the proportion of water quantity that satisfies 2 independent conditions, namely, water quality and water benefits. Although this fraction is conceptual and not real, it is essential for calculating sufficiency of a water use system, having in mind that the idea of efficiency itself is not something real, something physical. The terminology for the integrated pillars of a water use system is now possible by combining water path types given previously with usefulness criterion. For example, ET and NR are two consumptive water path types. By adding them together, the total consumption of a water use system is determined and is denoted by the symbol C. Applying usefulness criterion to C, useful consumption is calculated and is denoted as UC. In the literature and projects, water loss is calculated along the beneficial pillar as a water quantity that is not beneficial toward the objectives of a water system. However, in our approach, the quality pillar can also be added, meaning that water loss goes along usefulness, which considers both beneficial and quality attributes. In this broader sense, water loss happens due to non-useful water, equivalent to total useful inflow into a water use system minus total useful outflow from the same system, as shown in the equation. Total unrecoverable flow gives the total amount of outflow that cannot be reused by the same water use system during a time interval. It is the sum of water consumption and water loss, or the difference between inflow and return along the usefulness criterion, as shown by the equations. Both water loss and total unrecoverable flow are parameters of a water use system and not a water path instance. 3 levels of water use system have been defined, which in turn give 3 levels of sufficiency, namely micro, meso, and macro sufficiencies. Micro level is a kind of classical efficiency, which is flawed and should be avoided. Meso level gives the sufficiency of a water use system itself. And macro level is the same as meso sufficiency, and it also includes the main source of water, revealing its impact on the sufficiency of a water use system. The schematics of the 3 levels of sufficiency, composing of a water use system, and its inputs and outputs can be seen here. The general schematic of the macro level is presented with a river as the main source of water. Of course, the idea of the schematic remains even with other types of main source, such as groundwater. Sufficiency is an adaptation approach that promotes sustainable development. It is about sustainability because it integrates into its structure and consequently into management decisions the following dimensions of human interest. 1. Economics, such as agriculture, city, industry. 2. Social, such as population fairness. 3. Environment, such as climate, ecosystems. 4. Politics, such as institutions, stakeholders. For more details, please check the reference given here.